This is material from 8.8, improper integrals, and sorry, this should be clearer. This is something called the p-test, and I'm going to explain why this result works, but I kind of want to state it and then show you with a couple of examples. So I'm saying that when p is greater than 1, I get 1 over p minus 1, so the integral converges. And when p is less than or equal to 1, the integral diverges. So here's how I'm going to approach it. I'm going to use this example. P is equal to 3, so I'm saying this should equal 1 over 3 minus 1 equals 1/2. That's what I'm going to show you. So here's why. So again, with these integrals, when they're infinite, when they're improper, you take what's causing it to be improper and turn it into a limit. So I integrate, get x to the minus p plus 1, which is minus 2, over minus 2. Remember, that's minus 3 plus 1. Evaluated at b and 1. That's going to be equal to limit b goes to infinity, 1 over minus 2x squared at b and 1. I'm going to switch the limits of integration, get rid of the minus sign. So I'm going to write 1 over 2x squared, but I have to flip-flop that. I plug in, I get 1/2 minus 1 over 2 times b as b goes to infinity. This is going to go to 1 over infinity, which is 0. So what I end up with over here is just 1 over 3 minus 1, 1/2. Okay. So you could see, no matter what this is, we're going to add 1 to the exponent, and I'm going to get minus p plus 1 here. And since my exponent is going to be negative here, it's going to be positive down here. This term will go away, and I'm just going to be left with the 1 over p minus 1 here. So that would be true for p is equal to 4, p is equal to 5, p is equal to 2.1. It's the same process. So that's how we get this one here. Now, I'm going to use an example here. 1 over infinity, p is less than p is 1/2. That's a good one to use. So the square root. Okay, I'm going to say that the integral is infinity. So let's see why. Okay. 1 over b, limit b goes to infinity, x to the minus 1/2 dx, limit b goes to infinity. I add 1. Now since my p is less than 1, when I add 1, I'm going to get a positive exponent. Okay, and so this is limit b goes to infinity, x to the 1/2 over 1/2. So 2x to the 1/2. That's going to be limit, I'll write it down here, limit b goes to infinity, 2b to the 1/2 minus 2 times 1. So my r is 1/2. So that's going to go off to infinity. So I just get infinity right here. And so that diverges. So here's what's going to happen. When p is greater than 1, this exponent is going to be negative. And so that would mean when I get to here, that's going to always go to 0. I'm going to be left with 1 over p minus 1. Now when p is greater than 1, when p is less than 1, minus p plus 1 is going to be positive. So I'm always going to get a positive r right here. That limit's always going to go to infinity. So the upshot is, you can look at this exponent and know right away whether the integral diverges or converges. So let me give you an example. So let's say I have this question on the quiz. Does 1 over x to the 2/3 converge? Oops, I forgot the dx. Or diverge? If it converges, say what it converges to. If it diverges, say y. So here's what I would do. I would use the p-test. Using the p-test, p is equal to 2/3 less than 1. Therefore, the integral diverges to infinity by the p-test. That's all it would be. And let's say I got this one, 1 infinity, 1 over x to the 8 dx. Same question, does it converges, diverge? If it converges, say what? I would say since p is, less than or equal to 1, is equal to 8, greater than 1, the integral converges by the p-test to 1 over p minus 1 equals 1 over 8 minus 1 equals 1/7. That's all it is. So it's a really handy way to evaluate these integrals. Now, in section 9, chapter 9, we'll use this quite a bit. I'm sorry, that's supposed to be, it's x to the 8 right there. So p is equal to 8. And this is x to the 2/3, so p is equal to 2/3 here. Okay. Enjoy.